where we come together to learn, discuss, and explore the exciting intersection of reinforcement learning, robotics, and control. The name reward loop reflects what we are trying to build here, a continuous cycle of exploration, feedback, and growth, very much like reinforcement learning itself. Now, you may ask, why start a community like this? The reason is simple. Reinforcement learning and robotics are rapidly evolving, and it's impossible for any one of us to keep pace with all the new ideas, techniques, and applications on our own. At the same time, many of us are working in silos, reading papers in isolation, experimenting individually, and sometimes missing the bigger picture. A community like Reward Loop helps bridge this gap. It gives us a platform to learn from each other, to share perspective, and to stay motivated. We want this to be a space where students can understand papers better through explainers and discussions. Researchers can present their ongoing work and get constructive feedback. All of us can discover connections between RL, robotics, psychology, and even other fields that can inspire new directions. In short, our goal is to learn together, grow together, and create an ecosystem where knowledge flows freely. I am truly excited that we are starting this journey today, and I'm grateful to all of you for being here at the very beginning. For the inaugural talk, we are fortunate to have Mr. Sudhir Pratap Yadav from IIT Jodhpur, who will speak on learning for robotic manipulation, progress, and challenges. So, without further delay, let us begin the first session of Reward Loop. Please join me in welcoming our speaker, Mr. Sudhir Pratap Yadav. Sudhir, over to you. Thank you.
Hello everyone. Uh, Thank you for joining our community and talk. So without any delay, let's begin the first talk. So this talk is about learning for robotic manipulation. So basically we are going to explore latest research, what people have been trying to do, and we will see some few papers and what are the challenges that we have in robotic manipulation. So first, I will start with why manipulation is important and why should we focus on it. So the first argument is a evolutionary argument. As we know that humans are evolved from animals, and there are some theories which say that our brain expanded when we started using tools, and use of thumb was very important in our development of our brain. And there are other similar theories. So basically, what I want to say, there is an evolutionary argument of how manipulation itself helped to develop our own brain. Then there is a biological argument, which is something called homunculus, something like, and it is this the figure you are seeing here. It it is a, like a figurative human person, and the size of each organ that you are seeing here represents the amount of brain sensors that are attached to that particular organ. So as you see that in this particular case, the hands are very big, and it means that brain sensors required or interfaced with the hands are very large compared to other body, or very far in number compared to the other body. So these two arguments are from the biological and evolutionary perspective suggest that manipulation or moving our hands, finger, doing things in the world is very important, and it is the most part of brain is associated with doing these kind of tasks. Now I will start with some success of deep robotics, deep RL in robotics locomotion specifically, and I will show you quickly some few videos. So here you see this one robot is trying to walk on a slippery surface, and all those videos are trained using all these videos are trained using RL algorithms. And here you can see it is climbing on stair. Here you can see it is trying to jump a gap, and this is one from Deep Robotics. As you can see, it can do backflip, traverse very unusual and rough terrain, climb hills, and like can climb obstacle very good in very good way. So what I'm trying to say is these all are achieved using some kind of a deep reinforcement learning algorithms, and we will see how what is the recipe behind the success of these robots, and can we use the same recipe in manipulation. Before going there, let us also see few recent videos. So now same approaches have started working on humanoids. So here you see a Atlas robot doing some like walking, doing some locomotion. Here it is trying to walk in different way. Here you see uh, there was a recent some kind of a Olympics in China where there were many games. One of was racing, and here you can see unitary robot uh, racing. As you can see, it is very fast and quite stable. And here you see another robot doing cartwheel. So now you might be wondering, like, if we are able to achieve this kind of like success and these kind of robot behaviors using RL, then why are we not able to like do such thing in manipulation, or can have people tried such algorithms for manipulation? The answer is yes, people have tried this recipe for manipulation, but let's discuss what is this recipe that people are using to train robots, to train quadrupeds, to train humanoid to do very different and very amazing things. So what is critical for solving a task using RL? So first number is you require a large number of trials. So basically you require, because it is a trial and experiment, and like you trial, you do some experiment, you get some result, you do trial and error kind of learning. On every trial you learn something, you fail, then you learn, you get success, then you learn. So for that you require a huge number of trials. And question is how can we get so much number of trials, because in if you do it in real world, then it will be very expensive, cost wise also, time wise also, it will take human effort also. So the solution is the simulation. So all the previous videos I have showed you, they use some kind of a simulator, Isaac Gym or Mujoku or something like that, and then they train that particular algorithm in simulation, and then they transfer it to real world. So recipe is very simple. You have an environment in which we model the robot. There is a task defined, like for example, standing up, walking, jumping, doing cartwheel, something like that. And then there is a reward designed according to that particular task. And once the environment is ready, we use simple RL algorithms like standard RL algorithms, PPO, SAC, something like that. And then we train that algorithm and we get the trained policy controller. So people have tried applying this same recipe to manipulation also, but the first gap like the first challenge we find is something called sim to real gap. So reason being behind sim to real gap is two three reasons there are. First reason is precise model. So we do not have a precise model for a manipulation type of environment. So for example, if you want to do cooking, so we do not have a very good model of like how water will boil, what ingredients will, how will they affect our actions, like how are they affected based on our actions. So those kind of model. Also, let's say you want to plug a charger inside a hole, or you want to plug a USB inside a USB port. So it is very difficult to model these kind of where there is more interaction, where there are more contact points. The more number of contact points are there in a task, and the contact points are breaking and then non-breaking. So it is not uniform contact point. Like they are not always a contact point. The contact point forms and then it breaks. So those type of sim, uh, simulating those type of things is difficult. So this is one challenge. And we can divide this into mainly two domains. One is visual gap and one is dynamics gap. So visual gap simply means the difference between visual aspect of simulation versus the visual aspect of real situation. And dynamics gap is the dynamic aspect of simulation versus real dynamics of the real world. So, for example, I told you the cutting vegetable. How do you simulate cutting a vegetable, making a tea, cloth folding, all those things? And in visual simulation, how do you simulate different lighting conditions, different, let's say, colors, all like you need to simulate all kind of various kind of situations which you can see in real life. So this is very difficult to do and very time consuming and effort consuming. So there are some ways people are trying to address is one is better visual simulators, better dynamic simulator, domain randomization. So what is domain randomization is you try to uh, somehow like apply some pattern on the visual aspect. So you make, let's say you apply some green filter, red filter, you apply random lights and you try to distract the visual aspect of the simulator and then try to learn a policy on those kind of things. So one option is instead of using simulator directly, we can use real world, right? So even if we do not have precise model, so there was a one paper in 2016 where they tried directly learning on real world. So here task was very simple. It was just picking objects and it successfully like picked objects as you can see here. And it can even like push objects, pick objects out of clutter. So like what is the problem in this then? So the problem was scale. So for this particular task, as you can see that huge number of robots were used. So used and they were trained for like months and months and data was collected and they were trained and trained. So one issue of this is it's not just about like cost or money cost. Like you can, okay, you can invest in hardware or you can buy robots, but it requires continuous effort to make such setup to keep it working. Some robot damages, then you have to like maintain it. You have to replace some part. You have to reset the setup and all those kind of human effort is also required to collect this amount of data. And to do it for all imaginable possible tasks is very difficult. So this was just for picking one, like just for picking items from this particular box. That's the only task it was doing. So now second problem comes is even if let's assume that we have a precise model or we are either we are doing in real world, then second challenge is clear task definition and clear reward design. So even if we have a like a good environment, simulation environment, to define a task, what do you mean by task or what do you mean by successful task execution is very difficult. For example, in quadruped or the whatever examples I showed you, the task is very clearly defined. So let's say you have to walk. So in case of walking, people usually define the task by can you reach this position or can you achieve this velocity. So this is how they define the walking. In standing up, you can define, okay, can you achieve this particular torso height or are your center of mass is about some height threshold. So those kind of task definition can be used. But to define task for each and every manipulation like plugging USB, cutting vegetable, folding cloth, picking object, pushing things, rotating object in your hand. So like there are literally millions of tasks if you like do permutation combination of every manipulation task we do. So to define each and every task by a rule, like what particular task is, what is that task? To define each and every one by some rule is very difficult, and difficult also, and it is not. I think it is impossible to define everything. There will be conflicting definitions, so this becomes a challenge. And then designing a reward for each task. So if we look at some of the rewards from like previous previous successful training, then even for like standing up there are 5 to 10 rewards. Just to walk the robots there is 10 to 15 rewards. For example, joint velocity limits, to joint torque limits, how should center of mass behave, whether there should be a perturbation or not, what is the maximum velocity that you can apply, and what is the, and you have to then weigh each reward somehow, like what is the weightage of that particular reward. So defining all those kind of things is very difficult if you have to do it for all million of tasks. For particular one task maybe you can do it, for two tasks maybe you can do it, but for doing for million tasks it's very difficult. So, what comes to rescue? So, this problem has been there in earlier, as if someone recognize this is the same problem we have in computer vision. So, earlier people used to define objects using some rules. Okay, let's say this is a square, so it should have four lines, and there should be 90-degree angle between them. And people thought if we keep on defining rules and rules and rules over one over other and some logic, then we combining all those rules, we will somehow get computer vision. We will be able to, like computers will be able to recognize objects and so, and people have built massive libraries of rules over those kind of like things, but it never worked as good. So ultimately what worked is, you collect data and you show the computer this data, and computer itself figure out the rules. So this like classic machine learning. uh, and people have tried same thing in this manipulation and robotics. So instead of we defining the task or we designing the reward, why don't we collect some demonstration from humans, and that is the definition of that particular task. So then, so I will skip few of the slides because we have a huge number of
The
like slides to
generative
cover,
control policy is that
but you are getting the gist of the problem, like what is the main problem. So it is defining a task is very difficult. So one proxy we can use to define a task is a language. So language is a good proxy to somehow define a task. Like you can say, okay, pick red cube, pick green cube. So this little bit it gives some definition to the task. And then designing a reward is a difficult thing, as we discussed. So now, as I said, that instead of designing and defining the task, what we can do is collect the data itself from the human, and then we can get the definition of the task and the progression of the task from data itself. So that domain then falls into something called imitation learning. It is some kind of supervised learning only. So you can say it is related to very much related to supervised learning. So imitation learning means you collect some large amount of data, or not, even if not large. So let's say you want to do one particular task, you collect some data that for that particular task, and then you train some policy or train some policy to predict the actions that were taken in that particular data set. So your policy will try to align, like your algorithm will try to align your policy to the data set which was collected. So for basically the, for let's say you collected some images and you collected some actions for those particular images. So your policy will try to align, your algorithm will try to align your actions of your policy to the actions which were there in the data set itself. And the current, let's say I will say the state of the art in manipulation is imitation learning. So all the algorithms, all the videos you see in manipulation, mostly 99% of them are imitation learning things. And we will discuss few algorithms from imitation learning. Um, so idea is simple, you collect some data. So data collection can be done using tally operation. You tally operate the robot, and there are different approaches to collect data also. But we today we will not focus on them on so much, but we will focus on few algorithms, and then you train an algorithm and you get the policy out of it. Yes. So the first algorithm we will discuss is diffusion policy. So how diffusion policy works is, so before going into diffusion policy or any type of policy, there are some preliminary uh, imitation learning, something called behavior cloning. So what behavior cloning does, it just tries to match the distribution of your action to the distribution of action seen in the data set. So that's simple, like supervised matching. That's it. Now, what diffusion policy does is, uh, all recent imitation learning methods are somehow drawn from the generative AI or generative deep learning or generative machine learning algorithms. So what generative machine learning algorithms do is they try to learn the distribution of data sets. So for example, if you have a cat data set and you want to generate a new image of a cat, so what you do is you collect some images of that cat, and you then train a network which tries to predict the distribution of a cat. So it basically makes a probability, it learns a probability distribution of the cats. And whenever you sample from that probability distribution, you get a new image or you get a cat. So that is how it works. So uh, first, first policy, first algorithm we will discuss is diffusion policy. You might have heard about diffusion papers or diffusion generative AIs where people try to generate image. So those are based on some diffusion models. Similarly, here also there is a similar idea. So instead of generating images, we try to generate trajectories. So for example, we collect some trajectories using tally operation or something, and then we apply same process of learning the distribution, and we try to generate trajectory. So how diffusion works is, at initial level, at initialization, the prediction are random, so it just randomly predict anywhere what is the action, and then we try to denoise, or we try to denoise the, basically we try to denoise the predicting distribution to match the desired distribution. So as you can see in this video, initially the predictions are everywhere. So these, the dots you are seeing, is the predicted action. So what should be the action? So here you can see that, and we are not predicting just one action, we are predicting a sequence of action instead of just one action. So similar to like MPC or model predictive control, we are predicting a sequence of actions. So predicting sequence of action is usually more beneficial because it saves you cost and the actions are more coherent. So that's why it is more beneficial. So as you can see at this particular state, it is predicting some points. So these all points are sequence, which sequence where this particular endpoint should go. So before like going into it, let me quickly explain what is the observation, what is the action. So in this particular case, observation are images. So this particular image you are seeing, this is the observation, and the joint angles and the end effector pose. So these are observation, and action is end effector delta pose. So basically, where should this end effector move? Left, right, up, down, you can think in that term, or the position of the end effector, simply put. So this is action. And now this model, what it does is it takes the image and it tries to predict the actions. And how it does is, this is called the diffusion process. So initially it randomly says, okay, these are the possible prediction. But as soon as we start diffusion process, it iteratively denoise the this like all these predictions, and slowly you can see it start converging to right prediction. So this, now it converges to this particular prediction. Then we take some steps out of this predicted trajectory. So for example, the robot moves till here, and then again we predict the actions. And again, now it says, okay, this is your action. So it moves like this, and then again we predict the action, and then it predicts something, and then we move it, then again. So this loop continues, and this is how it works. So what are the benefits of like diffusion policy or from general behavior cloning? Is that since we are these all these methods, what we are using are generative AI methods or generative methods, and the benefits of those methods is they are very good at representing the probability distribution of data. So any data you have, you can represent it probabilistically very good using these kind of models. So for example, there is something called multiple modes in a data. So for example, in this particular case, you want to move from this point to this point. So there are two options. Either you can go from there or either you can go from here, right? So if you try to naively clone this, like naively match this model. So let's say you train a simple MLP and you say, okay, this is my state. I will just try to minimize the error between the outputs. So in this case, you have two possible output, this particular output and this particular output. So if you try to do mean square error, so it will give you something like in between, which is neither this, neither that. And it is neither correct option. So what I'm trying to say is, if you try to like do mean square error or simple naive like loss function, then this model, which the action which it learns, it will be some average something between them, and it will be not correct. It might collide with the object itself. So these models which we have are very good at representing multimodal data. What multimodal data is, for same state you have different kind of actions. So even those kind of representation is very good in this particular type of diffusion process. So it can represent those data. So as you can see, and other like other algorithms which are not diffusion based, that prediction is like either it is selecting this particular, it is very random, or it is noisy, it is some not. So in this case, as you can see, it is very good, right? Half trajectories are from left, half trajectories are from right. So that what I'm trying to say is, think of current imitation learning models, the let's say ki the power of these models is coming from the generative aspect of the deep learning and how to represent data. So any method which is good at representing data, multimodal representing data, can be used for this particular aspect. So this particular case we are using diffusion policy, and we can go technical, but here I would like to stop, and then we can discuss further things later. Next approach is action chunking transformer. Approach is similar. Basically, we will have some input observations similar like multiple camera angles, joint angles, and we will try to predict action sequence. So problem statement is same, but approach is little bit different. So this was one was using diffusion process. This is using chat GPT like architecture, so like transformer. So basically we will give sequence of inputs and we will get sequence of outputs. So we will, let's say, give n number of images, and history of images we also can give, and then we will get sequence of output. And same thing, instead of predicting just single action, we predict a chunk of action. It is a conditional VAE. So we can discuss what is conditional VAE, but what it means is the actions are conditioned on the observation. That's it. And features and the input features are image joints and something called latent variable Z, and it is related to the VAE part. And then output is simply the action sequence. So I'm skipping like much details, but otherwise it will take too much time to like complete the task, but we can discuss all the details later. But fundamentally what you have to get from this slide or this slide is, if we have some method which can represent the data distribution, then we can use that method to represent the trajectory distribution of some particular data set, and then we can sample from that particular distribution. And if we just represent all the data set, let's say we have data set of cat, and we sample a distribution of a cat, then it will generate some random cat, right? So that is called unconditional generation. But we do not want unconditional generation, we want conditional generation. Like, we do not want any random trajectory to be generated from data. We want that trajectory to be conditioned on something, right? So that is where condition came. So all these methods are conditional probability distribution. So this probability distribution is conditioned on observation. So the distribution will change based on observation. So that's how you can, like the trajectory, predicting trajectory will be dependent on the observation. So that's the major aspect you need to get. So we have two methods. One is diffusion and one is transformer to do same thing. And third thing which is we will discuss is something called VLA, vision language action models. And sorry for the typo. So this is vision language action model, and we will discuss one framework in this particular paper, which is called OpenVLA. So this is a paper name OpenVLA. So in these same the architecture is similar to this ACT architecture. Only thing added is, now instead of just conditioning on this image and like observation is image plus joint, we also add language in the mix. So now the generation of the trajectory will be dependent on image plus joint plus language. So the sampling part is now dependent on three things: image plus uh, language plus joint robot state, basically. So as you can see, this is the architecture. So here is the main transformer architecture. This Llama 27B you see is the transformer architecture, and this language instruction is converted into some tokens using tokenizer. Image is also converted into tokens using some CNN or some kind of feature encoders. So these are all some kind of neural networks. So every block you here see Dino version 2, SIGLP, this MLP projector, all these are neural networks which are basically converting this particular image to some numbers, simply put. And this llama tokenizer is tokenizers, which is converting this. You can think of it like which is converting this text into some numbers. So for example, one way to do is, we can there's a list of like, let's say, vocabulary, and each character is assigned some number, and then we just convert to that particular number. And then output, it also outputs some token, and then that token is again converted to this action space. So the action space is delta x, delta theta, and delta grid. So it is exactly similar to this particular architecture. Only different is now we add language, we throw language into the input. That's it. And little bit details, like in this particular case, one RGB image of this much resolution, language instruction. Output was 7 degrees of freedom. Other things I think we can skip for now. So these are the three approaches in imitation learning people are trying, and the most currently most excitement is in this VLA type of things, vision language action models, because now we can control the trajectory using observation plus using vision, sorry, plus using language. So for same image we can give two language instructions, and then the output will be different based on the language, right? So we can say pick this particular object, or we can say pick this blue color object, or this orange uh, pick place these things. So basically we are conditioning the action on language instruction plus image. And the data set that they trained is very huge data set. There are 2 million robot trajectories in the data set. Like as you can see, it is very different. And they do some kind of filtering, like only single camera point of view they select. They give some data weightage to how much weightage is given to that particular data set. So and so on. What I'm trying to suggest is here is like if you want to generate a like chat GPT level type of robot which can do everything, then we require a huge data set using this approach. So we have a good success using these algorithms. So let's start with some videos. So here you see a robot is trying to do some task. It is like tying the shoelaces. So what I'm trying to here I'm trying to show is like we can even learn very intricate tasks, very fine manipulation task we can learn. And each task you see here, we like the data was collected using tally operation. But this proves that if we have data, then that particular task can be achieved. And here you can see that it is picking clothes from this washing machine, putting it in the drawer, and then taking it and then folding the clothes. And everything is like autonomous. So all these things you are seeing is basically uh, done using imitation learning.
learning can be
I will skip few videos. So here you can see washing a dish. So and here you can see there is one innovative way to collect the data. So this paper introduced like you can wear this kind of a gripper and you can hold them, and there is a camera and IMU connected to this, and then you can collect data directly from here instead of using robots. So it makes the data collection easier and faster. And here you can see very uh, integrate or very fine manipulation task of trying to peel the banana. So all these tasks are roughly around like 2 3 years like recent. So let's say 2021 22 to 2030 24, around that period. And here you can see we have successful like task execution. So now the question is why I have written this partial success. So the reason is now we will discuss like why cannot we use this recipe and just like scale it to large. So now the natural question arises is why don't we have a robot GPT till now? First reason is the no internet scale robot dataset. Even with all like 2 million trajectories, people are collecting huge amount of data. There are factories literally, for example, in Tesla, there are whole body suit. People are wearing it and then collecting data set for humanoid. But it is very, very, very like what I say, ki cost costly, human effort is required, and it will take huge amount of time and effort. And the reason behind is this, because for example in ChatGPT or latest LLM, the amount of data that was collected, that was trained, it was trained on, is mammoth, like it is very huge. So to collect that much amount of data is very difficult, unless we have some kind of internet of robots, like where people are themselves putting data, because the data used in GPT was not was not collected by the researchers. It was already there, and it was not it was not made because we wanted to make a GPT. It was made out of some other internet grew, and people started texting and doing all those kind of things, writing. So it was like some kind of a fossil fuel, you can think. Like it was not made to be used for that particular purpose, but somehow we got that data. But we do not have that kind of data for to make some robot GPT or something like that. So question is, what if we keep collecting and collecting? So I don't think this is a like very good fundamental approach to solve this problem, because we do not have large data set. And even if we collect very large amount of data, still there will be some uh, I think that exponentially large amount of data is required to cover the spatial data compared to text data. So what I'm trying to say is there are more exponential diversity in spatial data. Like what I mean by spatial data is 3D data, visual diversity, trajectory diversity. For same task, you can do different ways, but for text, it is comparatively less. That's what I wanted to emphasize. So now to summarize the challenges, we have a something called sim to real gap, and it is vision gap and dynamics gap. Then we have difficulty using task specification and representation, and then there is no large scale data if we try to do imitation learning. So due to this sim to real gap and task specification, we cannot do RL. And due to this large scale data learning, we cannot use methods which are used in like self supervised learning or something like that. So there are some approaches people are working on. So these all the things we are discussing are around like say ki, roughly 2 3 years old. 2 3 years old, I mean 1 or 2 years old, but like 21 to 24, 23. But still people are doing it. It's not like old. But now people are trying to explore recent techniques. What are the new ways we can do manipulation? So we will explore few possible directions now quickly. I will not go into much details, but with just 5 minutes, we will try to explore what people are doing. So there are better visual simulators. So people are trying to create simulators. So instead of physics using physics to do it, people are using neural networks to learn a world model. And there are other methods. Then uh, instead of instead of using teleoperated data, people are using human data. So to use a large scale data, people are using human data. So videos on YouTube or on which humans are doing some work, they are using that to basically learn from it. And there are some other approaches, something called active exploration, lifelong continual learning, which are like basically instead of learning once, the robot keep on learning itself automatically. Like it just sees the world, do something, then learn, then keep on learning itself. So like on the task learning. And few papers in this direction are something called hierarchical decom. I have divided it into three topics, something called hierarchical decomposition. And in this, what we people are still using RL, but what they have done is they have divided the task into two phases, and they have limited the task. They are not doing for every task. What they are doing is there is a something called reaching phase. So the arm try to reach near the object, and then there is something called local policy. So this local policy is like in this particular case, it was pick only. So the RL algorithm is just trained to pick the object. That's it, and other part are taken care of with some using some other algorithm. Then there is something called vital. So it also has a reaching phase. This reaching phase is using some VLM or something like that. And there is a local touch policy. So the policy here also have touch sensors basically. Then there are some world models, something called Dreamer version 3, which use recurrent space model. Something it predicts the dynamics of the world. It predicts the rewards. So what is a world model in general sense is world model is something you try to make the model of the world. So what model of the world can consist is dynamic model of the world, visual model of the world, how task will behave, how action will predict. So you can predict different aspects of the world. Something there is a company called 1x which also have world models. It is an autoregressive model similar to transformer architecture, and they are using it for evaluation. So they are not using currently for training, but they are using it for evaluation. So let's say you trained a model, but how do you evaluate that policy? So instead of evaluating it in real world, they try to evaluate in their world model. And then there's something called VJPA. It is from Meta, and it is a joint embedding predictive architecture. So it is a different architecture from autoregressive, but the idea is behind is same. You try to predict the world itself. So world model is basically, instead of creating a simulator, we learn the simulator. Simply put, like this. So it reduces the sim to real gap. Simply put. And then there are few papers on learning from human videos. The one is Ego VLA. So in this, the egocentric videos are there. What egocentric video is? Let's say there is some camera attached to your face basically, and it is capturing your what you are doing. So those kind of videos. And then what they do is they retarget the human hand to robot hand using some inverse kinematics. So that is one way. So challenge in human videos is you need to like somehow retarget those trajectories to actual robot trajectories, right? Otherwise it will not match the how robot will perform compared to how human perform. One paper is something called point policy, and it uses some common point representation. So instead of image full image observation, it it selects few points, key points from the image, and then and same for it selects same key points from the robot itself, and then they try to make some the common representation. And so these methods are to learn from human videos. And conclusion of my talk is like, I hope I'm able to convince you that manipulation is important, and it is unsolved problem, and in other words it is research opportunity, and you should work in this area basically. Also, I would like to just in 2 3 minutes I would like to present some of my own experiments I'm trying to do. So here you can see I'm trying to like we are trying to pick a plate from dishwasher, unload the dishwasher basically. And this policy was fine tuned using a open VLA. So this was an open VLA architecture, and we fine tuned that open VLA on our own on our own data, and it worked little bit. I am just showing you success, but we had many failures also. Like it was very little, 2 3% success rate we were getting. And the other videos I am showing you are some of like we are trying to push a button. These are mostly using RL, and that this one was using imitation learning, opening a drawer and all those kind of things. And on we are also trying to do some work on the hardware side, and we have like made some data collection platform. We are trying to do it on UR5, and we also made some tally operation software which we can use using just mobile to collect the data to collect the data. So basically, when we move the mobile in a certain manner, the robot and effector will move, and we can close and open the gripper. And it is web based, so you don't require any installation or app installation. You can just directly go to the link, and it will you can directly control your robot. And later on we are trying to extend it to VR also. And all our research and codes and policies, everything is available online, and we believe in open source projects. And thank you everyone for listening to the talk, and I am now open for your questions and doubts. Thank you everyone.
Thank you, Sudhir.
Uh, Thank you, Sudhir. Now I would like to open the platform for questions and discussions. Uh, so if all the attendees have any questions, please go ahead.
I have one question. That in the past few months, I'm working on a manipulators and many game in my company. So I have a task to move follow some trajectory. But I am using mathematics, and mathematics also creates the problem of singularity.
Right.
But we use the mathematics because we need so much efficiency or accuracy like in microns. But can this RL problem, this RL solution can provide the solution of that problem?
Yes, so accuracy wise, I think it can provide a very good accuracy. So it depends on, I don't think I think we can get very good accuracy with the with RL solution. So that is true. Even the singularity part can be avoided. Like you can learn to avoid singular situations, but the same problem, like how do you design the reward around that, and how do you, and if you go towards the imitation learning route, then you have to collect the data for one task. So that is one solution. And I think the major problem with these tasks is the probabilistic nature of these tasks, right? So since neural network output is not deterministic, it is probabilistic. So the safety around that thing you have to consider. So there are some approaches which try to explore safe RL. But I will say if your task is very deterministic and require precise trajectory following, and you already know the trajectory, then I think it will be better to use traditional methods instead of RL or something like that.
Okay, okay. And there is also thing that in mathematics we can by using mathematics we can define that I have to move from that place to that place in that time and with that minimum velocity and that minimum acceleration. So all that thing by considering all these thing, it can be solved using RL, right?
Yes. So basically, basically you are saying we can apply some constraint on the problem, right? So the solution should be constrained by this particular constraint, right? Solution space should be constrained. So then you will do some kind of optimization. So RL is also a kind of optimization method only, right? RL is also doing some kind of optimization. Only the approach is different. So they use something gradient based descent and then some iterative trial and error. But the way to import, currently there are no, I don't think there are some research which are trying to impose hard constraints, like very hard constraint, but soft constraint can be definitely integrated in RL. So for example, you can say this is the maximum velocity limit I will allow, and then you can have some reward or some penalty if the your basically if your velocity limits exceeds this much, then you give some negative reward, something like that, right? And so same for time and everything, you can apply some reward. So this can be tackled in RL, I think.
Okay, thank you.
Okay. Thank you everyone for joining. We will be having our next talk on 13th of September. So see you all then. Bye. Thank you.